Okay, guys, welcome and thank you again for attending the Pulse Radiology Institute MR Registry Review. So what's on the docket for tonight is I'm going to go over intrinsic and extrinsic parameters and throw their trade-offs in there a little bit. There's going to be a little bit of MR math mixed in. We're going to go over pulse sequences, and then at the end, right when you're ready to, commit a heinous crime, stab yourself in the chest, I'll go over artifacts. And right at the end of that, right when you're ready to, I'm going to do the scan time formulas. Okay. So I'm going to jump right into it. Also, just so you know, I was looking at this material and I'm probably going to go a little bit past 9 o'clock. I hope to not go too long, but I just want to give you guys all a heads up now that I'm probably going to go a little bit long. So just so you know. All right. So let's see. All right. So we're going to share. And intrinsic, extrinsic parameters. Okay. Boom. Boom. All right, so intrinsic and extrinsic parameters is what we're going to go over right now. And hold on, where did it go? Come on, full screen, Stephen. Thank you. Okay, so intrinsic scan parameters are basically your contrast parameters. These are what's going to give you the T1, T2 proton density, contrast in your images. So the contrast parameters that I'm going to cover right now, TR, TE, TI, flip angle, and then echo train length. So you've got to know that changing any one of these can and will alter your image contrast, and you need to know and be familiar with the effects that they're going to have on image quality. So you need to know their definitions, and you're going to need to know the registry is going to be asking you, what are the consequences of your actions? If you do such and such with the TR, what's going to happen? If you do such and such with the TE, what's going to happen? So we're going to go over those right now. All right. The extrinsic parameters that I'm going to cover, field of view, scan matrix. We're going to go over isotropic versus anisotropic. They love to ask that. Receiver bandwidth next. And then this laundry list right here. I won't waste time reading them. So, we're going to cover image quality here a little bit. I'm going to go through some image quality things, what to look for, what makes a good image, what makes a bad image. So when you're scanning, all right, and your images come up on the screen, you need to do a quick little ask yourself, all right, is this a good image? Is this got the right contrast? Is it got good signal to noise? Is it got resolution? Okay. And the RADs will call you out on that. So you guys have been in clinical for a while, or maybe some of you guys are, you've done a decent amount of scanning. Radiologists love to, what, okay? So as far as the image quality goes, so this is the basic image quality triangle. Does the image have good contrast? Is there good signal to noise? Is there good resolution? All right. So and then I took the image quality triangle one step further, and I put my contrast triangle up the top to take the place of the word contrast. So the three main factors here are image contrast, sometimes called contrast to noise. Then there's signal to noise, SNR, and finally resolution. So our images need to have all three, okay? And obviously, contrast is king of the hill. Without good contrast, all the signal to noise and resolution doesn't do you any favors. Okay, so when your images come up, you want to say to yourself, do I have good T1, T2, or proton density contrast? And that's rather important in all images, all exams and all images, but it's really important in neuro work. So your contrast should be good if you're using your protocol right from your scanner. Sometimes you need to change things around a little bit, up the TR or things like that. But in general, your contrast should be good, but you still need to train your eye to know what is good T1, good T2, and good proton density. Do I have sufficient signal to noise? And I'll go over signal to noise. The first indication that you've got not good signal to noise is that the images are grainy. They look salt and peppery. That means you don't have a goodly amount of signal. Or you've got decent signal, but your noise went through the roof. All right. Then for resolution, can I see the structures that are there? Am I able to see the structures that they're looking at? And finally, the last thing that you want to say to yourself is, are my slices angled correctly? Do I have artifacts? And did I cover the entire anatomy? Okay. So any one of these, if you go, yeah, no, my contrast is no good, then you're going to have to run it again. If you didn't get good coverage, you're going to run it again. So you want to avoid that. So signal to noise, or SNR, or S/N, is the amount of signal to the amount of noise. So it's a ratio. How much of one do I have of the other? So signal is, in fact, the signal to noise, or your overall signal, is affected by multiple factors here. Field of view, matrix, which is pixel size, slice thickness, NEX, sometimes, so NEX is GE, acquisitions for Siemens, receiver bandwidth, and then your imaging coil, which we talked about last night. I won't go into that. Resolution is the ability to see small structures. Resolution is affected by these three factors right here. And your field of view, matrix, slice thickness, those are all going to adjust or change depending on your body part. So you're probably not going to be doing 5 or 6 millimeter thick slices through the pituitary. It's a small structure. You're going to adjust your field of view, matrix, and slice thickness to the body part. You're not going to do very small body parts. You're not going to do very small field of view on big body parts. You're not going to be doing a 200 field of view on a liver unless, someone's really, really small. So they are going to adjust depending on the body part. Okay. Now, signal. Here's one way to think of signal, or signal to noise. Know that signal comes from our pixels. I said this last night. We get signal from the pixels at TE. And the noise is random fluctuations or random non-useful, let's just call it what it is. It's random yuckiness, okay? And we get that from every place else, including the pixels, but we also get it from the electronics. We can get it from, if someone opens your scan room door and they break your Faraday cage, okay? So top left, signal comes from pixels. Top right, we get noise from everywhere else. And know that noise can change. It can go up and down during the running of the sequence, whereas the signal that we get from our pixels, consider it a constant, okay? So any given sequence is only going to give you so much signal, and then hopefully the noise is low. So that's what's going to give you a good signal to noise. So I've got highlighted here, as long as we're talking image contrast and image quality, okay? This is in my book. Most of you guys have probably seen this already. This is the image contrast triangle. So know that every image has some of all three contrasts in it. The basic contrast, T1, T2, proton density. Every image has some of all three. And what we're going to be doing is we're going to be using different combinations of TR and TE. I'll start off with those. And those are going to give us our image contrast. So whoever is up the top here, for example, T1, okay, we're going to be using a short TR and a short TE. So know that the short TR is going to increase T1 contrast in the image. And we're going to use a short TE to minimize T2. So because we use the short TR, T1 contrast starts to win. We're going to minimize T2. So we're going to leave one spot open for proton density. So this combination, short TR, short TE, makes T1 contrast dominate the other two. Same thing for T2. We're going to use a long TR. A long TR does not make it T2. Okay? Some people think that. No, a long TR is going to make it less T1. The long TE is going to add the T2 contrast into your echoes when they come in. So T2 contrast is going to dominate T1, and it's going to dominate proton density. And we're going to look at these images. We're going to pull them apart because I want you guys to understand when you look at an image, why there's contrast, why someone's bright, why something's dark. All right. Finally, proton density. We're going to use a long TR to decrease T1 contrast. So you're going to be using TRs in the thousands because you want to make it less T1. We're going to use a short TE because we want to minimize T2 contrast. So put these two guys down the bottom. Proton density is going to win the contrast war, as it were. Okay. Now, here's some images. Here's a T1 on the right, T1 on the left, T2 on the right. Okay. Now, short TR, short TE. You've got good gray and white matter differentiation. So the gray matter is this darkish, wormy stuff in the sulci. That's gray matter. It's dark because it's mostly water, and water has a long T1 relaxation time, like we know. White matter is mostly myelin. Myelin acts like fat, so white matter is going to be bright. So you've got bright white matter on a short TR, short TE. We've got dark gray matter, short TR, short TE. And then we have cerebral spinal fluid here, which is very dark. It's got a very long T1 relaxation time. So this right here is an outstanding T1 contrast image in the brain. Exact same slice, exact same patient. Now we've got T2, long TR, long TE. The long TR is going to minimize T1 contrast. The long TE is going to maximize T2. So the long TE is going to let fluid-filled structures get bright. And that long TE is going to let short T1 relaxing tissue basically get out of the transverse plane and not give you much signal at TE. So white matter here in the brain is dark because you knocked it into the transverse plane, but you waited a long TE and white matter got out of Dodge. It started going back to B0. There's not much of it in the transverse plane at TE, so it's dark. And because of the long TE and the long T1 relaxation time of cerebral spinal fluid and the white matter, because white matter here has got a lot of water in it, those are going to be bright. They stayed in the transverse plane, and at TE, they're bright. So this is a beautiful T1 on the left, a beautiful T2 on the right. Okay, any questions on that, guys? Okay, because I want you guys to have an eyeball to look at these, because you may get an image like this and they might say to you, what weighting is this image? And you need to look at it and go, okay, what's bright, what's dark, okay? And then proton density. Now, proton density is where a lot of people kind of struggle a little bit, all right? So we're going to be using a long TR because we want to decrease T1 contrast. We're going to use a short TE to minimize T2. So again, if you put the T1 and T2 down the bottom, proton density wins. So these two images right here are beautiful proton density weighted images. Know that proton density, basically, you're kind of letting everything be bright. So these images, both these images here happen to be 3000 TR and a 20 TE. Less T1, not hardly any T2. So whoever is bright on proton density has a high number of protons. So look at the cerebral spinal fluid here in the ventricles. and this is the putamen, I believe. No, caudate nucleus. So these two tissues right here are bright compared to white matter. White matter is dark. White matter has not relaxed hardly at all. This is an indication of who has a lot of protons in them, the CSF, and who doesn't have a lot of protons in them compared to the other, the white matter. So that's a beautiful proton density weighted image in the brain. All right, now let's get into some of the nitty gritty here. All right, so parameters, TR. So the definition of TR is the time from one excitation pulse to the next excitation pulse to excite the same slice. Key word here is same slice. The definition is not from one excitation pulse to the next excitation pulse. Nay, nay. It's from one excitation to the next that excites the same slice. So think of TR as a loop around time, if you want to think like that, okay? If you've got 20 slices in whatever body part, whatever weighting you want to think about, okay? You got 20 slices, for example. You're going to start imaging slice one, and then during the TR, during the time to repeat, the time of repetition, you're going to image all 20 of your slices before you go back to slice one. So it's a loop around time. During TR, okay, during the TR, that tissue is T1 relaxing. So do you give it a lot of time to T1 relax, or do you not give it a lot of time to T1 relax? What are some of the trade-offs of playing around with your TR? So if you increase the TR, you're going to increase your scan time, okay? The equation, which we'll talk about last thing tonight, is TR times phase times next. That's your basic scan time formula. So as TR goes up, scan time goes up. As TR goes up, T1 contrast goes down. As TR goes up, tissue heating, it doesn't go down, but you give it more time to T1 relax. Okay, you give it more time for that tissue to cool off because there's more time in between excitation pulses. All right, so know your definition of TR, know your trade-offs. So they'll ask you a question, all like this, all factors remaining the same. If you increase your TR, what will happen to the blank and the blank? So they like these twofers. So if you increase your TR, now you're going, all right, well, there's a couple of things Stevie just said. Look at your answers. If it says, if you increase your TR, you're going to decrease T1. Yep. If you increase your TR, you're going to decrease SAR or heating. Yep. So you need to know what your factors are. Okay. So look at the question, then look at your answers. One of those answers is what they want to hear, okay? And I know it's mostly ladies on the call, but it's kind of like talking to your husband. Tell him what he wants to hear, right? Yes, you can chuckle silently, and the guys in the background are saying, yep, like talking to the wife, tell them what they want to hear. Okay, so TR controls T1 contrast. It controls how much time each slice has to T1 relax. And know for sure, you got to know this, that tissue needs the T1 relax before the next excitation to give off signal at TE. If they don't T1 relax, they are saturated, okay? I'm going to go back a couple of slices here. Bear with me. Okay, now, here's a short TR and a short TE sequence, okay? Why is the gray matter dark and why is the CSF dark? This is a short TR and a short TE. The reason why they're dark is because they're basically saturated. We used the TR that was shorter than the T1 relaxation time of both these tissues. So they're dark. The T2 on the right, we used the TR that was very long. So we let the gray matter and the CSF fully T1 relax so that at TE, they can give us signal. Okay. All right. So they need to T1 relax. So theoretically, that the gray matter and the CSF is saturated by the short TR on the left-hand side. Okay. So they could also say to you, as all factors remaining the same, as TR goes up, what contrast is likely to develop? Proton density. Okay. Someone's got their mic open. If you could mute it, please, unless you've got a question. Thank you. Okay. Here's something else that you guys should kind of be aware of. SAR. Everyone goes, oh, SAR, specific absorption ratio. You should know those numbers. I didn't go over them, but know those numbers. 3 in the brain, 4 in the body. They can interchange SAR and B1 plus root mean squared. B1 is what? Your RF field, right? And the not plus root mean squared, but the positive root mean squared, that's the amplitude of your RF pulses. That's the root mean squared, if you want to think of it that way. So B1 plus root mean squared is how much RF any given sequence that you're going to run is going to expose the patient to. SAR is a federal limit to how much heating we can make happen in the patient. Okay, so the B1 plus root mean squared causes heating, and we need to stay under the SAR limits. Does that make sense to you? Okay, so SAR is across the board always the same for everybody. That's why we put a weight in when we register a patient. But the B1 plus root mean squared is how much RF is living in that pulse sequence that you are going to be running. Does that make sense, guys? Hopefully so. Okay, let's keep on going. TE. So TE controls T2 contrast. The definition of TE is the time from the center of the excitation to the center of the echo. That's the definition. As TE goes up, the amount of T2 contrast we're going to produce is going to increase. But the trade-off with increasing your TE is your signal to noise goes down because more vectors have left the XY plane. So the short T2 and the short T1 tissues like fat are going to start to get a little darker as TE goes up. But fluid is going to go bright. All right, so TE is T2. Sometimes they'll use the term 2 tau, T-A-U, 2 tau for TE. They'll interchange this. So know that basically 2 tau is TE. Tau means time. I think it's the Greek word for time. So how do we get 2 tau for TE? The time from excitation to refocusing is 1 tau. Refocusing to the echo is 1 tau. So from 90 to the echo is 2 tau. All right. All right. The short or fast T2 relaxing tissues like fat are going to have left the transverse plane. So here's a T2 curve right here. The red tissue, and I wish these colors were opposite, but the red tissue is a long T2 relaxing tissue like cerebral spinal fluid. It takes a while to leave the transverse plane, whereas blue would be fat, for example, and it leaves the transverse plane very quickly. So at this green arrow, if this, if you could take an echo at the green arrow, you're going to have bright CSF and darker fat, not dark fat, but darkish fat. Okay. The next intrinsic parameter is TI, time of inversion. You see these in IR sequences, in inversion recovery pulse sequences. So what's happening during the TI is T1 relaxation. So we flip everybody down into the 180, and then we turn off the RF and we let T1 relaxation happen. So the time in milliseconds from the 180 to the 90 in an IR pulse sequence design is the TI. And we change the TI to null or suppress signal from different tissues based on their T1 relaxation times. term that you're going to hear or see very likely in your registry is the null point. So basically, during the TI, whatever tissues get to the quote unquote null point, those are the ones that are going to be suppressed. So we're going to use short TIs to suppress short T1 tissue. We're going to use long TIs to suppress long T1 tissues. Know what the different tissues are. For example, what are some examples of short T1 tissues? All right, so short T1 tissues in MRI land are fat Gadden protein, FGP. You guys have heard that before. Fat Gadden protein are all short T1 tissues. They will all be suppressed by a short TI. An example of long T1 relaxing tissues would be cerebral spinal fluid and general fluids like edema, P, things like that. Those are long T1 relaxing tissues. So stir, short time, or sometimes short tau. Remember, time and tau can be, tomatoes, they can be interchanged. Flare is fluid attenuated inversion recovery. So as soon as you hear flare, you're going, fluid's getting suppressed. So an easy way to remember these is short suppresses short, long suppresses long, okay? So fat Gadden protein are short T1 relaxing tissues. IR sequences will suppress all tissues that have similar T1 relaxation times to the TI. So fat Gadden protein are all short T1 tissues. If we use a short TI, all three are going to get suppressed at TE. So do you guys typically, I'm just going to throw this out there, and do you guys typically use or run stir after you give gadolinium? Probably not, right? You're sitting there going, oh, I don't know. I've never noticed. Well, next time you do a sequence that you're going to give GAD, you've probably done your stirs first. Now, is that a rule? No, not really. Can you run stir after GAD? Yes, you can. Will you see the effects of the gadolinium on stir? No, you won't. Will the patient burst into flames because you ran stir after GAD? No. But just don't expect to see signal from gadolinium on stir because GAD is suppressed. It's got a short T1 relaxing time. Flare, long tissues like CSF, edema, and urine will be suppressed at TE. Does that make sense, guys? The TI is going to suppress tissues with a similar T1 relaxation time to the TI. Okay. Don't forget, guys, you got a question, lay it on me. Don't sit there silently, okay? If you got a question, ask. Another intrinsic parameter is your flip angle. 99.9% of the time when you hear or see flip angle, you're talking about a gradient echo pulse sequence. So you might see the term flip angle. You might see F/A for flip angle, or you might see this funny alpha with a little zero for angle, okay? All three of these mean the same damn thing, and that's called the nutation angle. How far are we knocking those vectors from MZ into MXY? As you increase the flip angle, you're going to be putting in a stronger or longer RF pulse. Usually it's stronger because longer, it could be a weak pulse and you turn it on for a longer amount of time, but everybody knows in MRI, it's all about tick-tock, right? So you're going to use a strong RF pulse to put in a big flip angle. All right. You can use a strong pulse, but barely turn it on, and you're going to get a partial flip angle. So the flip angle is how long or how strong that RF pulse is. So think of flip angle as the new T1 in gradient echo. So as you flip the vectors more into the XY plane, they have more T1ing to do. So they've got to go, and I'm just going to use 90 degrees here. It's not 90, but it's, you knock these guys all the way down to 90, they got a lot of T1ing to do versus if you knock them down only, say, 25 degrees. You're not going to see too much T1 relaxation differences between the tissues at 20 or 25 degrees versus if you knock them down 50 to 70. They got a lot more T1 contrast, a lot more T1 relaxing to do. So in spin echo, TR is T1. In gradient echo land, flip angle is the T1 along with the TE. So TE is TE is TE. Short TEs, less T2. Long TEs, more T2. A lot of times, they're being nice guys. I'm hearing lately that when they're talking about gradient echoes or T2 star sequences, they'll say bright fluid or dark fluid. And as soon as you hear dark fluid, you're thinking, T1. You hear bright fluid, you're thinking T2. All right, last but not least, echo train length. Echo train length is seen in fast spin echo or turbo spin echo. So fast spin echo is GE, turbo spin echo is Siemens land. The original term, when this pulse sequence first came about, this is how I learned it. It was called RARE, rapid acquisition from rapid excitation. So RARE, they might throw it in there at you, just so you know. All right. So the echo train is a series of 2 or more 180s, each creating an echo. Each 180 produces an echo, thus filling another line of K-space, filling more lines of K-space per TR, so scan time goes down. This word or should be per, okay? So we're filling more than one line of K-space per TR per slice. So your scan time is going to decrease by a factor of your echo train. Echo train, however, is going to influence image contrast. An increase in echo train is going to mean more T2 contrast production because the later echoes are going to get more T2. So the TEs are going to go up. So whoever's got their mic open, if you could please mute that. Thank you. An increase in echo train is going to mean those echoes are getting further and further away from excitation. So they're getting more and more T2. So your fluid's going to get brighter. Okay. High echo train is going to decrease scan time, which is a good thing, but it's going to increase tissue heating. Everyone says SAR, and it's been like that for decades. Everyone calls it SAR, but your B1 plus root mean squared goes up as echo train goes up. All right. Typically, short echo trains are for T1 weighting because we don't want to produce T2 to go into our K space. Long echo trains are going to be obviously for more T2 weighting, because the late echoes are going to increase or make the fluid even brighter. All right. So again, SAR or your B1 plus root mean squared is going to go up. So know that a 180 is 4 times the RF content of a 90. And it has to do with the size and shape of the parabola and all kinds of like Einstein stuff. But know that a 180 compared to a 90 has 4 times the RF. Now, again, I said these numbers earlier, but know that 3 watts per kilogram is your SAR limit for the brain and 4 in the body. Any reason why there's a difference? Who the hell cares, right? Well, the brain cares. It's more sensitive to heating. That's why you get a lower number, just so you know. All right. Echo train, one of the trade-offs besides scanning faster is blurring. The late echoes can start to introduce some blurring into your images. So a question here, it's in yellow. This is why I put it in yellow. Someone told me that they had this question on their registry. The images are blurry, but the patient is not moving. What scan parameter can be adjusted? And they're going to give you a list, okay? So if you said to yourself, well, what am I going to do? Am I going to increase the images are blurry. Should I increase my scan matrix? Nope. Because that's just going to make your scan time and your signal to noise drop. They're blurry. And the patient's not moving, but I want to scan faster because that's everyone's um, fix, right? If you decrease your TR, you're going to start messing with contrast, right? So the images are blurry, but the patient's not moving. You probably wouldn't, but the option there is to decrease your echo train length. All right. Any questions?
I have a question.
Please.
So you keep saying something that I'm just not used to hearing, and I don't really understand it. When you say that it happens at TE, I don't
Okay.
really understand what you mean.
Your echo. Okay. So and we're going to go over this in pulse sequences next, but at TE, at time of echo, that's when the signal is being generated in the coil. That's when that sine wave is going to start generating. You're going to stop making electricity in the coil. So as the protons here, let me do this. Hold on. I'm going to stop sharing for a second. Maybe this will be easier. Okay. Hold on. All right. So we're going to knock the protons into the transverse plane. We let them spread out a little bit. And then we're talking spin echo here. Then we're going to kick them in the ass and knock them over. And as they start to rephase, as they start coming together, as all these vectors start to come in, okay, more and more vectors are coming together, adding up, and you've got these moving magnetic fields that are pointing at the coil. So you start to generate more and more electricity in the coil through Faraday's law of induction. So as they come together, it's going to be hard to do this, but as they start coming together and pointing at the coil, you're generating signal. At TE, you tell the scanner, hey, turn on my coil and see who's giving me signal. All right. So
Okay.
at TE is when the coil gets turned on. And then what'll happen is that the echo is going to be happening for so long, then you turn off the coil. What's going to happen after that is they're going to start to spread out again, and they're going to start going back to B1, to B0. Does that make sense, Jess?
Yeah.
That helps.
Yes.
So
Thank you.
at TE, turning on the coil, all these guys, all these little vectors, these little magnetic fields, these little magnets are coming together. They're moving and they're pointing and they're adding up, and you're generating this sine wave of electricity in the coil.
Okay. Yeah, that makes sense.
Capiche? Okay.
Capiche.
Capiche. All right. Let's share again.
I have a question, Steve.
Yo.
Can you elaborate on the flip angle with the Ernest angle?
Oh, Ernst. All right. It's not Ernest. That's a movie.
Ernst.
That's a movie. Okay, hold on. Let me go here. All right, hold on. All right. So Ernst angle, okay, and Ernst is some German physicist guy, okay? Ernst angle, as soon as you hear Ernst angle, that's a partial flip angle in spin echo land. Okay? Not turbo spin echo land. It's typically used at, not typically, but you'll see it more often than you won't at 3T. 3T can be difficult to get good T1 contrast. So the Ernst angle is also going to give you the best signal to noise for a given TR. All right. So if you've got a short TR because you're trying to get T1 contrast, you're not going to use a 90-degree flip because you're going to start to saturate these tissues. You're not going to give them time to T1 relax. Okay. Does that make sense? Remember that? If they don't T1 relax, they're not going to be able to give signal. So it lets you drop your TR and only knock these guys down, let's say 70 degrees, and you'll get good signal to noise. You'll get good T1 contrast. Okay. Your scan time's a little bit less. You get good T1 contrast at 3T. So it's called an Ernst angle. I don't really go over it because I've never heard anybody asking about Ernst angle on the registry. I'm not saying it can't be there, but I've never heard of it.
Okay, I was just curious because one of the techs brought it up, but he took the ARRT.
Okay, all right.
Something about the Ernst angle and it being like an optimal angle?
Yes. So
Yeah.
the optimal flip angle for a given TR, and there's actually, if you Google Ernst angle, or if you go to questions and answers in MRI and you put in Ernst angle, they'll give you a chart. Okay. Don't memorize the chart. No, don't do that. You'll make yourself batshit crazy. Okay. Understand the principle of Ernst angle. Okay.
Okay.
Are they going to say, what Ernst angle would you use for such and such a TR? No, that's a bullshit question. And I would challenge that because that's not fair. Okay. Maybe if you've got an eidetic memory, maybe if you're Sheldon Cooper or Einstein and have this stuff memorized, but not for me and you. Okay.
Okay.
All right. So don't get crazy on Ernst angle. Know the principle. But again, don't look it up and try to memorize that chart because you'll want to hurt yourself. Okay. I'm just telling you. All right.
Got it.
Okay. Good question. All right. Where was I? Here we go. All right. Share. All right. So our extrinsic parameters. Now we're leaving contrast parameter land and we're into the geometric stuff. If you look at all of these, with the exception of like maybe these last four, slice, gap, concatenations, sap pulses, and flow comp, all of these guys are basically geometric things. I'm sorry, and NSA. So these guys right here, right at the top, these are geometry. How big are my pixels, basically? Okay. Are my pixels, big or small? Are they square? Okay. So let's talk about field of view first. Okay. Hold on. All right. There we go. All right. So field of view has a huge impact on multiple areas of your image. Okay. So it's going to affect image quality in resolution, signal to noise, artifacts, which we'll talk about, and actually in a very oblique way, your TE. So your field of view can affect your TE. Have any of you guys, maybe it's come up when you're scanning, if you drop your field of view a little bit, maybe, or even a lot bit, suppose you go from 300 field of view down to, I don't know, 180. I'm just throwing out numbers. Maybe you get a little pop-up that says, hey, Stevie, I got to up your TE by 2 milliseconds. And you check and you just go, yes, dear. And you continue, right? Have you gotten that pop-up ever before? You don't have to answer me. But if you have, that's because your field of view is affecting your TE. When you go to a small field of view, that comes from the field of view comes from the frequency encoding gradient. If you go to a small field of view, let's just say you go from 400 to 200, you're making that frequency encoding gradient work a little bit harder. You're making that gradient stronger, and it takes an extra millisecond or two to get to the amplitude that you need for that field of view. And your TE might bump out a couple of milliseconds. Okay, so a big field of view, the gradients are not working as hard. Small field of view, they're working harder, and it takes longer to get up to the amplitude for the small field of view. And I'm going to show you a visual on that in just a second, if I'm not mistaken. Hold on. All right, so how big the field of view is basically how big are your slices. You're going to use a big field of view for a big body part and a small field of view for a small body part. So when you think field of view, just stop thinking, oh, my slices. If I've got a 20 slice sequence, I got 20 fields of view. Okay, they're all together, they all move together, but think of it that way. So if you look at a loaf of bread, you got all these slices. Well, each slice is a field of view. Okay, field of view is measured. Typically, it's going to be either in millimeters or centimeters. So know that a 200 millimeter field of view, I believe, is it going to be GE? GE uses millimeters and Siemens uses centimeters, if I'm not mistaken. So a 200 millimeter is a 20 centimeter. Just know that. So the combination of matrix and field of view is going to determine pixel size. And we're going to do some math because they might say to you, what is your pixel size for this sequence? Okay. We're going to do some math there, okay? So field of view is a big killer or contributor to overall signal to noise. All right, so your pixel size is a combination of your matrix and your field of view. You're going to divide your matrix into your field of view, and that's going to affect your signal to noise. So your pixel size is going to have a huge impact on your overall signal to noise. So all factors being equal, and they can say this to you, all factors being equal, and here's where it they can't really ask you two variables. They'll say all factors being equal, and they'll give you one change. They can only give you one parameter change. They start throwing two parameter changes at you. That's not fair, and I would challenge that question. Okay, so all factors being equal, an increase in field of view is going to increase your pixel size and increase your signal to noise. But it's going to decrease, oh, I spelled spatial wrong. It's going to decrease spatial resolution, okay? And an increase in field of view is going to lessen the chance of the wrap artifact. All right. So changing the frequency matrix is going to change pixel size and shape. Okay. When you have a sequence that's running a little bit long, you go, oh, geez, I don't want to run this for, 5 minutes and 10 seconds. I want this, like maybe 4.5 minutes. What do? You knock down your phase matrix all the time. Everyone does it. I've done it a million times. Everyone does it. What you're doing is you're changing your pixel size. The pixel size get bigger, you get more signal to noise because there's more hydrogen in each little pixel, okay? All factors remaining the same. A small pixel is going to have a lower signal to noise because there's less hydrogen in it, okay? So the pixel size is a combination of your scan matrix and your field of view. You're going to divide your field of view by your matrix. And we're going to do that math, I think, right about now. Okay, so over on the right-hand side, we have a 200 field of view. And you're going to run a sequence with a 256. See this little number 256 squared. So 200 divided by 256 means those pixels are 0.7 by 0.7 millimeters. Okay. If you, for some reason, change your field of view to 400, they can ask you, what's your pixel size? So the pixel size for a 400 field of view, same matrix, is 1.56 millimeters. You're going to increase signal to noise. There's more hydrogen per pixel, but the pixels are bigger, so your resolution drops. So know your trade-offs, okay? Let me ask you this. If you double your field of view, you're going to double your matrix size, and you're going to get 4 times your signal to noise. So this right here, you go from 200 field of view to 400 field of view. Your signal to noise goes up by 4 times because we're doubling the pixels in 2 directions. You're doubling it left to right, and you're doubling it front to back. So now your pixel size is 4 times bigger, and you're doubling it twice. You're getting more pixels, more hydrogen per pixel. Okay. So with a bigger pixel, you're also going to get worse partial volume effect. And I'll go over partial volume effect soon enough. Okay. So you're gonna, if you double your concept, so how do you buy back that resolution? If you go from 200 to 400, you lose your resolution. How do you buy back that resolution? You can double your matrix. But when you double your matrix, what happens? Your scan time goes up by 2. Okay, does that sound like no phase wrap to any of you GE people out there? Well, if it doesn't, it should. And if it did, good. All right. Signal to noise and phase matrix. If you decrease the phase matrix to shorten scan time, you're going to make the pixels bigger. Like I already said, you're going to be lowering your scan time because TR times phase times next is your scan time. Lowering the phase matrix makes your pixels anisotropic. What does an mean? An means not. Isotropic means equal. So they're not equal in both directions. Anisotropic pixels decrease image resolution. They're going to increase partial volume. And here's something that they like to ask you. Isotropic pixels or voxels are ideal for what? 3D reformatting. So when you're doing MRA stuff and 3D kind of sequences, ideally you want isotropic pixels or isotropic voxels to do your 3D reformatting. All right, some pixel math. So they very likely are going to ask you to figure out your pixel size. So again, field of view divided by your matrix. If they're nice guys and they give you 256 by 256, you only have to do the math once. If they say your matrix is 192 by 256, now you got to do the math twice. So 280 divided by 256, 1.09, and then 280 by 192, 1.54. So your pixel size is 1.09 by 1.45. Okay. They might say to you, what kind of pixels are those? Are they isotropic or anisotropic? Well, iso means they're the same. Anisotropic is what this is right here. You don't have pixels the same size in 2 dimensions, okay? So iso means the same. If you look it up in Webster's, which I did, okay, it means properties of the same value. So iso means square, so 2 by 2. Isotropic voxel is 2 by 2 by 2. And means not, like I've already said to you, okay? So it will very likely ask you to do pixel size. They also love to ask you to calculate voxel volume, okay? Voxel volume is, I'm going to go over in just a minute. So when you've got isotropic versus anisotropic pixels, the trade-off of having anisotropic or having isotropic is image quality. You get less blur with isotropic because you're talking a square grid for phase and frequency locations in the Cartesian coordinate system. You're going to get better resolution. But most techs always go, their plan A is to drop the phase, which gives you anisotropic, which is going to increase blur, decrease resolution, and give you more partial volume. Everyone does it. I've done it a million times. It doesn't make it wrong. But the trade-offs are, like I said, you need to know what the trade-offs are. Now, what's partial volume? I've used that term a couple of times. Maybe you guys know it. Maybe you understand it, but you're going to get it again. Okay. Know that the signal intensity of any pixel is the average of all the signal intensities it contains. Okay. So if a pixel is bright, it probably has a lot of high signals in it. It might have some lows, but it's mostly got high signals, so it's a bright pixel. If the pixel has both high and low signal intensity, that pixel is going to be gray. It's not going to be bright. It's not going to be dark. It's going to be somewhere in the middle. So basically, partial volume is an average of all the signal intensities in that pixel. Okay? All right. A voxel. Well, what's a voxel? A voxel is a pixel with depth, a slice thickness. So they very likely are going to give you a question and say, find out the pixel volume, the pixel size here. And then they'll say, what is your voxel volume on such and such a sequence? So then you've got to go through this math problem, find out the pixel size, and then multiply it by your slice thickness. So, for example, okay, we've got a field of view, and you're going to divide it up by your matrix, and you get a pixel of, let's say, 0.78 by 1.45. And your slice thickness is 3 millimeters. So now you're going to multiply 0.78 by 1.45 by 3, and that's going to give you 3.39 cubic, guys, watch this, cubic millimeters. Okay, that's your voxel volume. They love to ask that stuff. Okay, you will be able to use a calculator. So, don't think, oh, crap, I've got to remember how to do this short, longhand. No, you'll have a calculator. All right. They can ask you pixel area. Okay. Find your pixel size and then you multiply by itself. So a 1.45 by 1.45 pixel, it covers an area of 2.10 millimeters squared. That's area, that's height times width. There's no volume here. An anisotropic pixel, same thing. Multiply the height by the width, and it's cubic millimeters. Square millimeters. My bad, guys. All right, so watch these little 2s and 3s, okay? So cubic means it's 3-dimension. The 2 means it's 2-dimension. All right. Scan matrix and signal to noise. I've kind of beat this to death already, so I'm just going to keep on going. All right. Receiver bandwidth. Everyone gets confused about receiver bandwidth. And if you're a little bit shaky on it, you're not alone. Okay. So when all's said and done, the receiver bandwidth is a sampling rate. Now, I'm hoping, and I'm pretty sure that these guys on the registry are going to use narrow and wide to describe receiver bandwidth. Why are they going to use these two? Because Siemens uses hertz per pixel to term their receiver bandwidth. GE uses kilohertz to describe their receiver bandwidth. Philips uses water fat separation. 3 manufacturers, 3 different terms. They all mean the same thing, but it's like 3 different languages. So to make it easy, hopefully on you guys, it's wide and narrow. All right. So a wide versus narrow. Wide receiver bandwidth is a fast sampling rate. So you're going to sample the echo fast, or you're going to sample the echo slow. So my analogy that I use is narrow is 20 miles an hour. You're going to sample the echo, or wide, you're going to sample it at 60. So you've got a certain amount of work to do to sample that echo. Are you going to do that work at 60 miles an hour or 20 miles an hour? Okay. 20 miles an hour is going to take you longer. So you guys should have this chart memorized. Forget about the motion. I threw motion in just because, but forget about the motion. Don't try to memorize all 6 of these. Try to memorize one of them. Pick one that you like. I don't care. Not my circus, not my monkeys. Pick one that you like. You say, oh, well, I like the narrow bandwidth. Cool. The narrow bandwidth, all factors remaining the same. If you go to a narrow bandwidth from wide, you're going to up your signal to noise. And I got some pictures I'll show you. If you go to a narrow bandwidth from wide, you're going to increase chemical shift artifact. Okay. Oh, got a chat here. Hold on. Alonda, no, they have their place, and I'll go over that. That's a good question, and I'll go over that. And mostly it's because of signal to noise and TE. Okay, so if you go to a narrow bandwidth from wide, you're going to increase your minimum TE. Okay, because the narrow bandwidth is a slow sampling rate. It's going to take you longer to sample that echo. Your minimum TE goes up. Remember what the definition of TE is. It's the time from excitation to the center of the echo. If you're taking your time sampling the echo, that TE goes out a couple of milliseconds in time. And I'll show you what I mean by that. Hold on. So know your trade-offs. Memorize one, and the opposite is true. So if you go, I like narrow, everything goes up with the narrow bandwidth. So therefore, wide bandwidth, everything goes down. All right. So here's your echo. The red line is the echo, and the black line is random noise. Okay. So if you use a wide receiver bandwidth, the reason why you lower your overall signal to noise is because you're sampling everything, okay? You're sampling out here in purple where the signal to noise ratio is in the tank. It's in the garbage. So you got low signal to noise included in your K-space. You got low signal to noise included in your K-space. Your overall signal to noise drops. But you wide bandwidth, you're done with this echo quickly. So your minimum TE goes down and your chemical shift goes down. Down below, narrow bandwidth. You say, I'm going to take my time and sample this echo. Very good. So now you're sampling from here to here. You're excluding this crap low signal to noise part of the echo. So overall, you're only sampling the sweet spot of the echo with narrow. But the trade-off to get that high signal to noise is a longer minimum TE and a worse chemical shift artifact. Okay, so just memorize one, and the opposite is true. So when I say you got all the sampling to do, okay, do I have that picture in here? No, I don't. Okay, so your frequency matrix, in your scan matrix, you've got a phase and you got frequency. The number of your frequency matrix is how many times you're going to sample this echo. So let's suppose you're going to sample it 256 times. That means the analog to digital converter is going to go na 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 na. It's going to sample 256 times across this echo. Okay. Are you going to sample those 256 data points quickly, or are you going to sample them slowly? If you sample them quickly, you're going to be done with them. Maybe your minimum TE is 10 milliseconds, just for shits and giggles, okay? But you go to a narrow bandwidth, now your minimum TE goes up to 12 milliseconds because you're sampling slower. So the question was, when do you use which one, okay? You can use any one anytime you want, doesn't matter. You can do that. But typically, you're going to use your wide receiver bandwidth on T1s, typically. Can you use a narrow bandwidth on T1? Sure. Patient's not going to die. They're not going to burst into flames. You're not going to quench the magnet. The wide receiver bandwidth is going to minimize, or you're going to get a shorter minimum TE. What is TE control? T2. If you want T1 contrast, you don't want T2 in your K-space, right? So on T1s, you're typically going to use your wide receiver bandwidth to minimize your TE, to minimize T2. The wide bandwidth is going to cause an overall lower signal to noise, all factors remaining the same, but T1 weighted images typically, pound for pound, have a higher signal to noise than T2s. So you kind of got a little signal to noise to burn. So you can do that wider bandwidth to get the shorter TE at the sacrifice of signal to noise. Does that make sense? So the opposite is on your T2s, your stirs, your fat sats, things like that. Things that are signal starved. Those are your T2s, stirs, and fat sats. You will typically see a narrow bandwidth. The narrow bandwidth is going to bump up your signal to noise because you're losing signal from the fat. Fat is a major contributor to overall signal to noise. So if you're doing fat sat or stir, your signal to noise is in the toilet anyway. I need a narrow bandwidth to maximize the little signal to noise that I'm going to get. Does that make sense? Okay. And on your T2s and your stirs, a little bit longer TE, it's just fine because you want T2. Okay. Does that make sense? Does that help you out? Okay. So that's when that's how typically you will see the wide and narrow bandwidths on different pulse sequences, depending on what the weighting is. Okay. Next, NSA acquisitions. All 3 different manufacturers, 3 different terms. We got GE, we've got Philips, and we've got Siemens. Basically, a NEX or an NSA or an acquisition is how many times are you going to fill your K-space? So you're scanning and you're going to fill are you going to fill your K-space once? You're going to fill it twice? You're going to fill it 5 times. The scanner doesn't care. It will do whatever you tell it to do. Okay? Your scan time is going to go up, but so will your signal to noise. So all factors remaining the same, going from 1 nex to 2 nex, you're going to add 40% or 0.4 signal to noise. You're going to get 40% more signal to noise, but at the expense of twice the scan time. If you say, well, I still need even more signal to noise, okay, I'm going to go from 1 to 3 nex or NSAs or acquisitions. The square root of 3 is 1.7. So the square root of 1 is 1, 1.4. So going to 3 nex from 1, you're going to add 70% signal to noise at the expense of tripling your scan time. So it's a square root equation. All right. Now, if I'm going to spend the time and scan and fill my space twice, why don't, if I'm going to fill my, hold on, I just lost my mic. Okay. If I'm going to fill my K space twice, why don't I get twice the signal to noise? Because don't forget, noise is random. The first acquisition you run out of 2, maybe you've got low signal to, maybe you got low noise and high signal. On your second acquisition, you still got the same amount of signal, but now your noise came up. So now you've got 2 acquisitions with 2 different amounts of noise. So it turns out to be the best fit being a square root. So that's where that comes from. And they like to say, you know, if you need to double your scan time, if you need to double your signal to noise and you're using 1 nex, how many nex do you have to do? So you'd have to go up to the 4, which is a square root, gives you 2. So you would double your signal to noise by going from 1 to 4 nex. All right. So far, so good, guys. All right. Slice thickness and so slice thickness is measured in millimeters. Everybody uses millimeters. Okay. The analogy that I use is how thick do you get your ham or your bologna sliced at the deli? There's a couple of different ways to change slice thickness, but it's typically going to be a slice select gradient amplitude that's going to change your slice thickness. Okay. So there's 2 ways to change your slice thickness: transmitter bandwidth and slice select gradient. But typically you're going to use your slice select gradient. So here's what I mean by that. Okay. So we've got a transmitted bandwidth, 63 megahertz plus or minus 5. So that means you got 63 in the middle and there's 5 hertz on each side. If you use a shallow slice select gradient, you've got a thicker slice. If you use a high amplitude slice select gradient, you're cramming all those frequencies into a smaller cross section. You get a thinner slice. So this is just a visual on what the slice select gradient will do for you. And so when you change slice thickness, this is what the scanner is more than likely doing. Okay. So here's slice thickness again. All right. So we've got 63 megahertz plus or minus 5. So there's 5 on one side and there's 5 on the other. So that's a transmitted bandwidth. How tightly are you packing them into a slice? Is it 3 millimeters? Is it 5? Is it 10? That comes from the amplitude of the slice select gradient. You're cramming them in here. You're in the city. You're in downtown New York. Everything's crammed in. It's really tight. Or are you in Minot, North Dakota, and you've got a big field of view and everything is spread out? So what does slice thickness do? What are the trade-offs? So remember one of them, and the opposite is true of the other. If you got a thick slice, you got increased signal to noise. There's more hydrogen per pixel. Resolution goes down because your pixels are bigger. The pixels are thicker, your voxel is thicker, and increased partial volume effect. And the opposite is true. Thin slices do the opposite. Now, what about this partial volume thing that I talked about? So partial volume effect gets worse as slice thickness goes up. 3 millimeters versus 5 versus 10. Partial volume is an average of everything that's in each one of these. So if you've got a small dark object in a 10 millimeter thick slice, it's going to get averaged in, and it's not going to change the signal intensity of the pixel. Okay, so it's an average of all the signals within the voxel. And remember, when you're talking, two axials in the brain, those pixels, they're actually voxels because they have a slice thickness. They have a left to right, like say 1 by 1, but if there's a slice thickness, that's a voxel, even though you're not doing 3Ds, okay? All right, slice gap is basically how much tissue are you skipping? So you can actually skip tissue in between slices. That is actually an accepted method. Okay, it's called a distance factor as well. There's gap or distance factor. A larger object like the liver, you're going to have a higher percentage of gap. A smaller object like pituitary or IACs, you're going to have a smaller gap. Okay, this is a Siemens scanner, and it just shows you, here's the distance factor. You can just up it and put more tissue in between. Here's a visual on how you would get gap, and you change the gap by changing the center frequency of your slice. So you can just move a slice over a little bit and not image some. So basically the tissue that's processing here at 69, 70, and 71 megahertz, it doesn't get an RF, so it doesn't get imaged, and that's a gap in between slices. Or you can image everything. See how these numbers all match? It goes from 68, there's no gap. It goes right from 69. So the next slice is butted right up against. There's no gap. All right. We already beat that to death, and we already talked about that. Concatenations. What are they? The definition of concatenation is when things are grouped or linked together in a way to produce a particular effect. In MRI, we use the word concats. It's concatenations, but it's concats. And mostly it's used to get you your image contrast. And the example I like to use is everything that we do in MRI during a sequence has to be done during the TR. So all your slices, all your RF pulses, your echo trains, everything has to be done within the TR. So if you have a big stack, let's just say 40 slices, you need to scan, say, a humerus from shoulder to elbow, and you need 40 slices, just for yucks, okay? That 40 slices may require 1,000 TR or more, but you can't do T1 with 1,000 TR, correct? So what happens is you say, well, I'm going to do 2 concatenations, and the scanner goes, yep, Steve, no problem. It'll do 20 slices at 500 TR, and then it will do the other 20 slices at 500 TR. You get your 40 slices, you get your contrast from 500 TR, you stay in T1 land. You could do 3 concats and split it up and do it in thirds. The scanner gives you all 40 slices in one sequence, but it splits them up in 3 packages, I guess you'd call it, okay? Does that make sense? Does that work for you? Okay. SAT pulses is another part of your extrinsic parameters. We've all done this. We've all used SAT pulses, put them all over the place. You can place them, you can angle them, you can overlap them. It's not a big deal. So what happens is, here's a line diagram. You got excitation and refocusing. There's an RF pulse that gets put in ahead of everything. So this tissue gets basically an excitation pulse, okay? What was that? Yes, Aldana, yes. So concats allows you to increase the slices basically without increasing the TR, correct? You got it. But it's a way to maintain contrast. Okay, good point. Okay.
Is there a downside to increasing concats?
Scan time. You still get the same scan time as 1,000 TR. Like my example used 40 slices and 1,000 TR.
Mhm.
You still got the 1,000 TR scan time, but you got the 500 TR contrast. Does that make sense?
No,
No. Okay.
no.
So hold on. Let me go back. Hold on. I want you guys to understand this. Okay.
Like I use it, but I don't really know
Right. So your
what
scan
I'm
time
doing.
goes up. So for example, okay, you need to do a big stack, 40 slices, but 40 slices takes you out of T1 land. Oh crap. I can't. So you can either do two small stacks of 20 and 20, or you can say, keep my 40 slices and do two concatenations. And the scanner goes, yep, Aldana, no problem. And it will scan half the slices at 500 TR, totally done. And then it will go back and do the other 20 slices at 500 TR until they're all done. And then it groups them all together. You get one set of images of 40, for example, and they're done at 500 TR. So you maintain your T1 contrast with the short TR, even though it would have taken you 1,000 to get all 40, you still get your 40, but it's done in half stacks.
Okay.
Yay, nay?
Yeah, because usually when I increase a concat, I then decrease my TR.
That's something, that's another way, but be careful with decreasing your TR too much. So if you say, oh, well, if I can do halvesies and drop my TR, I can go to 3 concats and I can do a much lower TR. What are you doing if you drop your TR too much? You're saturating tissue.
Right.
Yeah. So that's one of the downsides of bumping up your concatenations. Yeah, you can go to the lower TR, but you're going to start to saturate. Okay. That
Yep.
makes sense. Okay,
Yep.
cool. All right. So SAP pulses is an RF pulse that you graphically put in. You guys have done this a million times. I know you have. Okay. And it just puts in a wide transmitted bandwidth right here, for example. And that tissue got an RF pulse ahead of the regular imaging sequence. Okay. So here's your spin echo, for example, but it got an RF pulse before it got the excitation pulse. So this tissue right here that's in the red box got 2 excitation pulses very quickly. No time to T1 relax. What happens to that tissue when it doesn't T1 relax? Saturation. So you don't get signal from this tissue only. You can use it for motion control. You can use it for artifact control. The problem though is it is RF and it does increase your RF exposure to the patient within the sequence, and it could possibly cause you to up your TR. Because remember, like I said earlier, everything we do in MRI has to be done within the time constraints of the TR. And if you can't, you either have to bump up your TR or use concatenations. But this way, SAP pulses is a way to make signal from a certain area or a certain region within your field of view, make it go away. All right. GMR and flow comp. I'll try to go through this pretty quick because I can already tell I'm going long. Okay. The translation for flow comp is and GMR or GMN, it's basically a way of decreasing pulsatile flow artifact. And it uses a pair of bipolar gradients, which is basically going to bump out your TE. So GMR and flow comp, one of the trade-offs is a longer minimum TE, because this work, I'm going to show you a picture of this. This extra work is done before the TE, so the TE bumps out. So you're going to have basically, and if you look at this math, -1 +2 -1, these are just representations of gradient pulses. So the -1, a +2, then a -1 comes out to 0. So your gradient motion refocusing or compensating for flow. So here it is, and you're looking at this and you're going, oh crap. All right. follow me on this. So the A lobe, okay, is a gradient pulse and it dephases things, okay? Anytime you turn on a gradient in MRI, stuff is going to pick up phase. It gets messed up. It's what it does. Okay, so you're going to say, well, I don't like that, so I'm going to compensate for that. And that's the BC right here. So what you're going to do, this is part of the pulse sequence. It's there always. You can't do anything about it. Okay, so this gradient gets turned on and messes things up. So I'm going to overcompensate with a +2. So here's a -1. Below the line is minus, above the line is plus, and the height is amplitude. So a -1. Then we're going to turn on a +2 to overcompensate. And then we're going to turn on an opposite polarity, a -1. And at TE, things are going to be in phase and you won't get that pulsatile flow from veins. And you see that a lot on the long TR and the long TE sequences. Stir is horrible for the pulsatile flow. You guys have seen it. You see that little white dashed line, not an RF leak, but that little pulsatile line, something like this. Okay, this is a T1 axial post-GAD in the brain. See this stuff going like this? Okay, that's pulsatile from GAD, unfortunately, but flow comp can help knock that down a little bit. That's what flow comp does. The turn off or the turn down of it is it makes for a longer minimum TE. Okay, so these graphs here, this is my last slides here. This should not be new to you. Okay, this stuff should be, you should have this in the front of your brain all the time. Okay. And I'm not going to run this list because I've already done it. I've done all of these already. Okay. Let's take 2 minutes. I'm going to stop sharing. Let's take 2 minutes and we'll come back. Yeah, let's come back at 8:25, 2 minutes, quick pee break. And then we'll finish up for the night. Okay. Let's see, can I pause? Okay. So let's see. I want to share pulse sequences. All right. I want to try to catch up a little bit, guys, because like I said, I can already tell we're going to go long tonight. All right. All right. So pulse sequence design. What is a pulse sequence? We're going to hit these guys right here. All right. Spin echo, fast spin echo. Pretty sure I think I took drive out of there. So we don't have to talk about it. Gradient echo, 2 and 3D, IR, echo planar, time of flight. All right. So what is a pulse sequence? Well, a pulse sequence, I teach that there's 2 basic kinds of pulse sequences. There's spin echo based, SE, and there's gradient echo based. And all the other pulse sequences that we are going to talk about tonight are variations on these 2. All right. So your basic spin echo pulse sequence is spin echo is a 90 and a 180. So if you look at a line diagram, and for example, if someone says to you, identify this pulse sequence, first thing I want you to do is look for a 180. If there's a 180, that's spin echo based. If there's not a 180, it's gradient echo based. And we'll go on from there. So a pulse sequence is a rigidly timed series or sequence of events. There's RF pulses, there's gradient pulses, and there's echo formation. Now, this particular line diagram comes courtesy of Siemens Medical. I don't want you to think that I did this. I've had this for decades. I've been using this one. Okay, so we have excitation pulse. That's what kicks off everything. Okay, we talked yesterday about FID, free induction decay. So when we turn off the RF, that's when these guys initially spread out. We don't capture this signal. It happens too quick and it's too small and it's only half the echo anyway. So it happens and we don't collect it. But what we can do is we can refocus this and make it come back with either an RF pulse in spin echo land, or we can use a gradient application to make these guys refocus. Okay, so the FID is really half of an echo. So looking at a line diagram, there's always an excitation, and then if there's a 180, it's spin echo. We have gradient pulses here, gradient slice, gradient read, aka gradient frequency, and then GP for gradient phase. Notice that these guys are timed with some RF, and they're timed with the echo. These lumps or these domes above the line mean it's a positive polarity gradient. Below, it's a negative. And the length of time, because time runs from left to right, that's how long the gradient is on for. Notice the phase. We've gone over this in my pulse sequence class. Notice that there's lines here. That means that every TR, the amplitude of the phase encoding gradient is changed. These guys here, slice and readout, are constant. Phase changes every TR. What changing the phase encoding gradient does is it causes this echo, future echo, to go in a different line of K-space. So you've got your RF pulses that are timed with gradient pulses, and the readout gradient read is sometimes called the frequency, or frequency is sometimes called the readout gradient, because this gradient is turned on when the echo is being read. That's when the analog to digital converter is turned on. So as long as you're reading the echo, this frequency encoding gradient has to be turned on. Okay. Now, note that the slice select gradient and the RFs are simultaneous. So we're exciting the slice, then we're going to phase encode it, and then we're going to refocus the slice. Same gradient, same amplitude. Okay. Notice how big this RF pulse is here compared to this one. Technically, there's 4 times the RF in here. So if you notice that difference on a line diagram, that's why. Okay, so we're going to excite, phase encode this future echo. We're going to refocus the pulse, refocus the slice, and then turn on your gradient, your readout gradient during the echo. Okay, so then this echo is going to go into a line of K-space. Yeah, I thought I resumed recording. Let me double check here. Hold on, thank you. Let me stop sharing for a second. Yeah.
It says recording on my
Yep.
screen.
Okay. Yep. Thank you. I would be really annoyed, thank you, if I messed that one up.
Where is this recording going to be available?
Mandy is going to put it on Canvas. It's going to go in the student resource center.
Okay.
So,
Jessica and I aren't students there though.
yeah, I know. Unfortunately, yeah. There's a couple of you guys that aren't students and are not going to have access.
Oh.
So, well, you're PULT students, but they're not PRI students. So unfortunately, we'll have to see if what we can do about that. I'll talk to Mandy. But anyway, okay. Let's keep on going here. Okay, so I've enlarged this, so you'll notice that this phase encoding gradient has multiple steps versus, say, the readout gradient does not. So what this means is that if you've got, for example, 256 phase encodes in your pulse sequence, you're going to do 256 lines of phase. You're going to have 256 different amplitudes of this phase encoding gradient. In regular spin echo, you're going to need 256 TRs. You're going to have 127 negative pulses. You're going to have 128 positive. And if you do the math quick, you're going to say, wait a minute, those two don't add up to 256. That adds up to 255. There's one TR where no phase encoding gradient is applied. So there's your extra one. So that comes out to 256. But that's what this means. You're changing the amplitude of the phase encoding gradient. Okay. Looking at a line diagram, like I already said earlier, look at it. If there's a 180, if there's a 90, 180 complex, it's spin echo. If there's a 90, so see this one here, this is a trick, okay? But there's no 180, so that makes it gradient echo. So this right here just means this is less than or equal to 90 degrees. A gradient echo typically has something less than 90 degrees for an excitation pulse. It can be 90, you could, you don't, but you could. Okay, so don't let this throw you. If you look at this and you go, wait a minute, it's a 90. Look, spin echo has got 90. This is 90. Look at this little, I forgot what they even call this symbol, but it means less than or equal to 90. So the presence of or lack of a 180 determines what pulse sequence it is. Now, this is a basic spin echo, okay? I showed you this symbol before. Here's the flip angle. This could mean 90. That's fine, okay? But don't let this throw you. Don't go, oh, well, that's a gradient echo. No, there's a 180. So just be mindful, okay? So this is a 2D spin echo line diagram. Why is it 2D? I'll tell you why it's 2D. Because there's one phase encode gradient, okay? There's one set of gradients that looks like this. So that means that Fourier transform, when K-space is filled, Fourier transform is going to do two calculations. Fourier transform is a mathematical algorithm, and that's about all I know about it. It will do two calculations on this data set. It will do one for phase. It will do one for frequency or readout. Two calculations, 2D. If you see a line diagram like this and you go, oh crap, there's two of those things. Good. 2 means 3D. Okay. 1 means 2D. 2 means 3D. Fourier transform will do calculations on slice, phase, and frequency or readout. So that's 3D. There's a lot of 3D sequences out there nowadays. It only basically used to be 3D time of flight, but now the manufacturers are developing all kinds of 3D spin echo. Okay, and that's fine. 2 means 3 and 1 means 2. So when you see these, you go, oh, that is a 3D spin echo pulse sequence. Just so you know, that's how you interpret those, okay? Now, I said earlier that TE can also be called T2 tau, okay? And here's a way of showing. So from 90 to the refocusing, okay, is 1 tau, or TE over 2, half TE. So that's 1 tau from here to here. And then it's 1 tau from here to here. 1 and 1 makes 2. Another thing that they have also seen, and I've heard this, that the refocusing mechanism is applied symmetrically within the sequence, which means it's applied at half the TE. So if your TE is 20 milliseconds, you're in spin echo land, for example, if your TE is 20 milliseconds, the 180 is turned on at 10 milliseconds. So it's applied at half the TE or symmetrically between the 90 and the echo. So 2 tau. Fast spin echo is 90, 180. You go, all right, there's spin echo. Oh, wait a minute, hold on. There's multiple 180s, there's multiple echoes. So that is a fast spin echo turbo, or also called rare, like your steak. I like my steaks medium rare, but that's me. So rare is interchangeable with spin echo and turbo spin echo. So you are going to be filling multiple lines of K-space per slice per TR with fast spin echo. Regular old everyday spin echo, right here, you're filling one line of K-space. There's one 180, there's one echo, you fill one line. Very inefficient time-wise. It's a one line of K-space per slice per TR. Fast spin echo fills multiple lines of K-space per slice per TR. So your scan time goes down with the echo as a function of your echo train length. You will typically use short echo trains for T1 weighting because each one of these echoes gets more and more T2 because you're getting further away from Queen to 90. Okay. If there's another echo out here, it's getting further and further away in the timeline. It's getting more and more T2. So the downside or one of the things that we have to manage with fast spin echo is we have to manage the multiple echoes coming in. So it's still fast spin echo. Your scan time is still short. You got an echo train, but you've got to declare or you're going to tell the scanner what your TE is. The TE in fast spin echo is also called the effective TE, and that's telling the scanner which one of those multiple echoes do you want in the center of K-space. Now, K-space basically has three zones. We've got the center zone, which is where you get most of your image contrast. So remember, CC, center lines give you your contrast or your weighting, WEIGHTING, weighting. The outer lines contribute mostly to resolution, a little bit of contrast, but mostly resolution. And there's another term for resolution, and it's called edge detail. So if you see the word edge detail, they're talking resolution. Now, I just had a thought, and I'm going to add this in. Resolution, here's a question that I've seen asked before. They're going to give you all these parameters, TRs and TEs and matrix and slice thickness, and they can say to you, what is your in-plane resolution on such and such a sequence? And you go, crap, what is in-plane resolution? Very easy. It's just slice thickness. Okay, so you cannot resolve a 2 millimeter, or you can't resolve it well, a 2 millimeter lesion in a 10 millimeter thick slice. You don't have the in-plane resolution. You need thinner slices. Okay, so your in plane, which means your slice thickness resolution, is limited to how thick your slice is. I'm going to have to add that in. Let me write that down. I want to, okay. In plane resolution. Okay, going to add that in for next time. All right, questions, guys? Okay, so your fast spin echo, you're going to run, like I said, you got multiple echoes per slice, per TR, and you want to put the good stuff. Your effective TE goes into the center so that they contribute mostly to the image contrast. The least desirable echoes, meaning the ones that are not your ETE, go in your outer lines. So they're not bad, but they're just kind of the least desirable ones. Okay. So remember, center for contrast. And the low amplitude phase encoding gradients is what's going to put your echoes in the center of K-space. Okay. So your center lines get filled from your low amplitude phase encoding gradient. Those equal your center of K-space. Your high phase encoding gradients go in the edges for edge detail. So here's what a fast spin echo looks like real quick. Okay, we got a 90 and a bunch and several 180s. Here's each 180 causes an echo. These right here that are the lower amplitude phase encoding gradient is going to put these echoes in the center of K-space. So that's what I mean. You're going to have high amplitude echo, a high amplitude phase encoding gradient. This echo is going to go to an edge line. These low amplitude echoes are going to go in the center of K-space. Now, here's a question, and follow me on this, and I'll spend an extra couple of minutes if you don't get it, okay? we are filling these lines of K-space by changing the amplitude of the phase encoding gradient. A low amplitude phase encoding gradient causes the highest amplitude echo because you're not screwing things up so bad, okay? A big, strong gradient is going to mess things up. It's going to cause things to dephase worse. So low amplitude phase encoding gradient puts stuff in the center of K-space, and you're going to have the highest amplitude echoes. High amplitude phase encoding gradient puts them in the edges of K-space, and because it's a high amplitude gradient, it screws things up a lot more, and you get lower amplitude signal to noise. So here's where I'm going with this. They've asked this question. The low amplitude data, low amplitude echoes in K-space represent the blank amplitude and represent blank, while high amplitude data echoes represent what? Okay, this is kind of crazy. Okay, low amplitude data echoes, that's these guys, low amplitude represent what kind of gradient, while the high amplitude data echoes represent what? So the low amplitude represent spatial resolution, and the high amplitude represents your contrast. Okay, so the answer to this one would be B, and I'm spending extra time. Anybody have questions on this?
Yeah, I'm confused about that one.
Okay, so very good. That's fine. So center for contrast. In order to have this echo go in the center of contrast, the center lines of contrast, you're going to use low amplitude phase encoding gradients. The low amplitude gradient causes them to have a high signal to noise or a high amplitude. Look at the amplitude of this echo right here in the middle versus the amplitude of this one on the edge. Okay, this one in the middle is a high amplitude echo, and it came from a low amplitude phase encoding gradient. That's why it's in the middle. Low amplitude in the middle, low amplitude gradient equals a high amplitude echo. So far, so good? Then look at the amplitude of this one echo right here compared to either one of these in the middle. This is a low amplitude echo, and it's in the outer edges because we applied a strong or a high amplitude phase encoding gradient. That's what put it out here. And because it was a high amplitude gradient, it's got a lower signal to noise. So it's a low amplitude echo that comes from a high amplitude gradient. Okay, high amplitude gradient gives you a low amplitude echo. Low amplitude gradient gives you a high amplitude echo. They've asked this question. That's why I threw it in here. I wanted to go over it because you look at this and you go, holy crap, Batman. Whenever you turn a gradient on in MRI, you screw things up. You make tissues dephase. When they dephase, they have a low signal to noise. So far, so good. So a strong amplitude gradient is going to cause a low amplitude echo. This high amplitude gradient goes in the edges of K-space. Just remember one of these, or try to remember one of these, and the opposite is true. Okay, and I'm on Facebook. Maybe some of you guys have seen me. I'm on Facebook, and this was a question that someone asked. They said, this was on my registry. And I went, oh crap, I gotta steal that. So I stole this from Facebook from someone who had it on their registry. Okay. Do you want me to go over that again? Don't be afraid.
Yes.
Okay, so while you're running the sequence, okay, a high amplitude phase encoding gradient is going to cause a low amplitude echo, because the high amplitude gradient makes things dephase more. So at TE, they're not all together. They don't have their shit together. So the amplitude of the echo is lower because of the high amplitude phase encoding gradient. The high amplitude phase is a resolution line. So it goes to the edges. So low amplitude data echoes, boom, right out here. Low amplitude echoes, low amplitude data in K-space represent what? Spatial resolution. They're on the edges, okay? So low amplitude data comes from high amplitude gradients. That's edge detail, so resolution. While the high amplitude data, the high amplitude echoes represent contrast. Okay, so the answer to this question is B. I'm going to move on. Okay, think about it. We can come back to it later on if you like. Okay. All right. So echo trains, I've already said this, echo trains are going to cause multiple echoes, filling multiple lines of K-space per TR per slice. So the long echo trains are going to cause more T2, and you're going to use them for T2 weighted sequences. You're not going to use a long echo train for T1 because long echo trains cause T2 contrast. You don't want T2 contrast in your T1 weighted K-space. So short echo train, T1. Long echo trains are used for T2. And again, the longer the echo train, the lower the signal to noise, and the more T2, the brighter fluid is going to get. Okay, gradient echo. As soon as you look at this, you look at a line diagram and you go, what am I looking at? What do you look for? You look for a 180. There's no 180 here. Even though this shows a 90, don't let that throw you off. Or they might put that little funny A or alpha with the degree. If there's no 180, it's gradient echo. Now, a gradient echo pulse sequence is sensitive to the big three: main magnetic field, local magnetic field, and susceptibility differences. These guys cause dephasing to speed up a little bit. Those protons in the transverse plane are going to dephase on their own, but these three here make it speed up. They kind of add to it, as it were, okay? And without the presence of a 180 at TE, you're going to see the effects of the big three. So in spin echo land, we have the 180. It puts everything together at TE, okay? In spin echo land, when you're going to knock them down, you let them dephase, spin echo puts them over and puts them all together. Everybody is together and in phase at TE. So the effects, the additional effects of the big three are not shown hardly at all. Whereas with gradient echo, okay, you're going to knock them in. Let's just keep it at 90 for now. You're going to knock them down. You're going to let them dephase. You're going to dephase them by turning on a gradient, okay? And you're going to make them dephase a little bit. Then you say, okay, enough of that. Let's refocus that. You reverse the polarity of the gradient, and these guys come together. But they don't fully come together because this gradient reversal doesn't correct for the big three. So you're going to see worse susceptibility artifacts. You're going to see worse artifact from local field inhomogeneities. You're going to see worse artifact because of the main magnetic field inhomogeneities. Okay, so that's why it said that gradient echoes are more susceptible to the big three. Okay, so you might see a line diagram like this and you go, you're looking at it and you go, what's that little funny A? And I don't see a 180, so that's got to be gradient echo. Remember, the flip angle is the nutation angle. Another name for it. So you got conventional spin echo, 90, 180. Don't let this little less than or equal to 90 throw you. Look for the 180. All right. I've already been 2D and through 2D and 3D. All right. Inversion recovery, flare and stir. Okay. Already talked about it. Stir, short time inversion recovery or short tau. Flare is fluid attenuated inversion recovery. You're going to have a TI in both of those. The TI is adjusted depending on what tissue you want to suppress. Flare and stir, they both end in IR. They're both basically the exact same pulse sequence. It's the same order of events. It's just different timing. Okay, so here's a basic inversion recovery. So before the inversion, everybody's lined up with B0. After the inversion, everybody is now pointing the opposite direction. Okay, so here's your line diagram. Here's your inversion pulse, and here is your TI. During the TI, T1 recovery starts to happen, and you want to get whatever tissue you want to suppress at the null point at the end of the TI. So when the TI runs out, the 90 comes in, that's whatever tissue is in the null point at the end of the TI is going to be suppressed. Now, watch these blue and yellow arrows here. So here's stir, short time inversion recovery. We want tissues to get to the null point. So we're going to knock everybody down, okay? During the TI, fat is going to T1 relax because fat is fast, right? During the TI, water basically doesn't do anything. It just basically stays in the transverse plane. Then the 90 comes in, all right? So the 180 knocked everybody down. In between the TI, fat recovers to the null point. Then the 90 comes in, and what happens is water is going to get knocked from 180 into the transverse. Fat that was at 90 gets another 90 and gets knocked down to 180. Okay, that's the effect of the 90. Then we're going to refocus. Water is going to get knocked over to the null point or the transverse plane now, and fat is going to get knocked into the longitudinal. Now at TE, who's going to give you signal here from this set of arrows, from these net magnetization vectors? Who's giving you signal at TE here? Remember, this is stir. Who's giving you signal? Someone chime in.
Fluid.
Yes, fluid. Because of the T1 of fat and the TI, they match, we nulled the signal from fat. That's what stir does. Guess what? Flare does the same thing. Okay? Flare does the same thing. Follow those yellow and blue arrows. I'm going to blow through this real quick. So the 180 knocks them all down into the negative longitudinal. During the TI, fat goes all the way back. It completely T1s, because don't forget the TI is long. Okay? During the TI, water gets into the null point. Then the 90 comes in. What happens? Fat gets knocked into the transverse. Water gets knocked down to the negative longitudinal. Then the 180 comes in. Water gets knocked into longitudinal again, and fat is in the transverse plane. At TE, fat gives you signal, water does not. Okay. Questions on that, guys? It's a nice visual to see them. Okay. Trust me, I worked hard on getting those arrows to spin on demand in the direction, okay, that I wanted them to. Where does the TI come from? They love to ask this question as well. What TI do I use? Well, what tissue do you want to suppress? if you multiply the T1 of a tissue by 0.69 or 69%, that number you get will be the TI to use, and you'll suppress that tissue. Okay, so for example, the T1 of fat at 1.5 Tesla is around 220 milliseconds. You multiply that by 0.69, you come up with 151. So at 1.5 Tesla, you guys are probably using around 150 Ti, and that's going to suppress fat. Same thing. So at 3T, same thing. You multiply the T1 of fat, which is now raised up to like 280 or so, multiply it by 0.69. You're probably using a TI of in the 190 to 200 millisecond range to suppress fat at 3T. So my question here is, why does the TI lengthen at 3T versus 1.5? What's the big difference between these two fields? What happens? T1 relaxation gets longer at 3T. So you need a longer TI. So there is no definitive TI. Very common TIs at both fields, but there is no one TI that fits both. Okay, just so you know, T1 relaxation gets longer at 3T versus 1.5. So remember, for TIs, short suppresses short, long suppresses long. Okay, look at this line diagram. What's your initial reaction? What kind of curve is that? You look at it, you go, well, it's T1. You know, yeah, sorta, but it starts down below here. Okay, so it starts down under here. It doesn't start where the green is, it starts down here. So that makes this an IR curve. It's basically a T1 curve, but it starts down and down the bottom. It starts from below because we knocked everybody from alignment with B0 pointing up. We knocked them all pointing down with the inversion pulse. Okay, now you've got T1 and T2 flare. The big difference between T1 and T2 flare, they both got similar parameters, except the T1 flare has a short TE. Remember, TE controls T2. So you're going to have a long TE for T2 flare. You're going to have a short TE for T1 flare. Just so you know, don't get crazy trying to memorize these numbers, because they're kind of fluid, but just know that T1 flare has got a short TE. Okay. All right, we're gonna blast through that. Okay. Real quick, when you go T2 flare, if I've got T2, why don't I have bright fluid here? Here's a T2 flare. Because the flare IR uses a long TI. Where's my TI? Here, 2300 milliseconds. That long TI suppresses CSF. Okay, you've basically got the same kind of T2 contrast. You got bright gray matter, dark white matter. Bright gray matter, dark white matter on regular T2. But the TI is what makes the difference. The TI suppresses the CSF. Okay. Identify these pulse sequences. Which one is on the right, on the left here? Okay, 180, 90, 180. That's inversion recovery. Can you tell whether that's stir or flare? No, you cannot, because there's no TR, TI, TE. There's none of that stuff. This is inversion recovery. Over here on the right, that is fast spin echo. Multiple 180s, multiple echoes. EPI, or echoplanar sequences, are typically spin echo, 90, 180. Echoplanar, the characteristic of EPI sequences is there's a big string of gradient reversals from the frequency encoding gradient. Each one of these reversals causes an echo. So you're filling all the lines of K-space in one TR. That's what echoplanar means. Echoplanar imaging. It's basically a huge echo train without the RF pulses. You've got gradient reversals. So it's a combo spin echo and gradient echo. DWI. DWI is echoplanar. What's the difference? Well, first of all, you went, okay, this is spin echo. All right, that's cool. Look at all these reversals, all these echoes. Yep, that's echoplanar. What the hell are these guys right here? These are DW gradients, diffusion weighted gradients. They are meant and designed to, what did I say earlier? That gradients screw up and cause tissues to lose signal to noise. Yes? So in echoplanar, specifically DWI, we use gradients to not null, but lower the signal from tissues that are moving, okay? So we are going to be imaging, we're going to get our contrast, our DW contrast from tissues that are moving things on a cellular level. So the general rule in MRI is that when you turn on a gradient, tissues lose phase, and moving tissues lose even more phase. And when they lose phase, you lose signal at TE. So DW gradients work on something called Brownian motion, okay? Stationary tissue will be somewhat affected by turning on a gradient, but tissues that are moving stuff in and out of the cell, Brownian motion, AKA sodium pump, you've got stuff that in the cell that's moving in and out and through the cell membrane. So moving tissue, as it were, in the cell is going to lose signal. It's called Brownian motion. When the tissues lose their blood supply, a stroke, you're going to lose your ability to move stuff, and that's called restricted diffusion. So as soon as you see restricted diffusion, you start thinking stroke. Okay, so normal tissues will lose more signal on a DWI because they're moving. Non-moving tissues, stroking stuff, will lose less signal. So you got something that's bright next to something that's dark. Now, you guys that are my students from before, you've seen these images. The left-hand image here, the dark tissue pointed out by the yellow, is normal tissue. It's got diffusion. It's got its Brownian motion because of those gradients, because of these guys right here. They dropped in signal. Tissue right here with the red, it's not moving. That water in the cells is just sitting there stagnant. You don't lose signal. So you've got bright next to dark, and that equals what? Contrast. Okay, so you're going to have a B1000. Typically 1000 is your B value for a stroke in the brain. So you've got tissue that's moving, good, nice and normal. Tissue that's not moving stuff around has restricted diffusion. It's bright because it doesn't lose signal because of those extra gradients. And then there's something called an ADC map. It's analog, apparent diffusion coefficient map. When these two tissues match, the rad will call that a stroke, okay? This area here is bright, matches this area here that is dark, they'll call that a stroke, okay? What's the B value? I use that term. A B value is a number that quantifies the amplitude of the diffusion gradients, the length of time that they are turned on either side of the 180, and the time in between them. A high B value is going to be more sensitive to restricted diffusion. So high numbers, high degree of sensitivity. Low numbers, low degree of sensitivity to finding or imaging restricted diffusion. Time of flight. We're almost done with this, guys. Okay, I know I'm going long. I apologize. Time of flight MRI. Okay, time of flight MRA. We're imaging that as blood flies into the slice, it gets excited, refocused, and we get signal before it flies, before flying out. So that's called time of flight. Another term for time of flight is flow-related enhancement. So blood signal is enhanced because it's related to the flow. Flow-related enhancement, time of flight, tomatoes, tomato. They can be used interchangeably. Okay. How does time of flight work? It works because we are using extremely short TRs that saturate stationary tissue. Remember, tissues need to T1 relax before they can give signal. If the TR is too short, stationary tissue, the muscles and the bone and the tendon and all that stuff saturates. But we're using a very short TE to capture the blood before it leaves the slice. So we've got bright blood or bright blood flow next to dark background, and that's MRA contrast. Okay, so as the blood is flowing, we've got fresh spins coming into the slice so that we've always got fresh, new, bright signal in the blood. Okay, blood flow is bringing in fresh, unsaturated spins. Okay, so we're imaging the slice, spins come in, they get imaged, they leave. Fresh spins come in, at TE, they give signal and they leave. Okay, fresh spins come in, give signal and leave. So this stationary tissue is dark, but the blood is fresh, bright blood, and it moves. New blood comes in, it's bright, it moves. Does that help? Does that work for you guys? You guys have seen this slide before. Okay. That's why we get bright blood vessels and dark background tissue. Now, know that blood is bidirectional. What goes up must come down, right? So we've got the heart beating here. Blood is flowing up into the slice. Blood is also flowing down in the venous side. With this kind of scenario, we're going to see both veins and arteries. And you only want to see one side. So that's when you're going to put in a saturation pulse. So you're going to want to see only one side. You don't want to see both. We're going to put a sat pulse in on the side that you don't want to see. So here's an example. We've got blood here in the chest and the heart coming up the carotid arteries. The yellow is the slices. We've got venous blood coming down at the same time. You're going to put a sat pulse above so that venous blood coming down is going to get RF before it comes in and gets more RF. So it saturates the venous blood coming down. Okay. They love to ask this kind of question. Where do you put the sat pulse? Are you above the heart or below the heart? So here's carotids. You guys have done carotids. Heart's beating. Here's your region of interest, whether it's 2D or 3D. Blood is coming in, going to get imaged. It's going to be bright. Sat pulse above. The blue is the venous blood. It comes in, it gets RF. It brings that RF with it, and it's going to be saturated in the slice because it got too much RF too quick. Below the heart, it's opposite. This is the kind of question they love to ask. Do you want to do a venogram in the iliac arteries? Where are you going to put your sat pulse? They have asked that question before. So you have to be logical and say, well, iliac, that's below the heart, and the arterial blood is moving down, not up. And the venous blood is coming up, not down. So you're going to put the sat so that you take out the arteries, and you're going to and the sat up here is going to allow the veins to be bright. So just be mindful. You have to stop and think for a second, okay? Am I above or below the heart? And which side do I want to see? And that's where you're going to put your sat pulse, okay? All right, guys, I know I blasted through that real quick. I'm going to hit artifacts, and then we're going to call it a night, all right? I appreciate your patience, guys. This did go a lot longer than I thought. Okay, artifacts, real quick. So artifacts are nothing more than false information in your image. There's multiple sources of artifacts. Either comes from the patient, it can come from the physics of MRI, or it can come from our electronics. So mostly what they're going to probably do is they're going to show you an image and say, what kind of artifact is that? Okay. So artifacts have some direction. So if you're looking at this, you might be going, okay, what direction is that in? Okay, what is that? What is it causing and things like that? So which is your phase and which is your frequency direction? It's important that you know which directions go, which artifacts go in which direction. So again, they're going to show you an image and say, what artifact is this? As far as the ARMRIT registry goes, what I like about the way they ask the questions is they group them together, for example. So let's just say you sit down and you're going to start taking your test, and you're going to get all your artifact questions. For example, you might get all your artifact questions asked first. So maybe there's 20 artifact questions. Well, once you get through your artifacts, you're not going to see any more artifact questions. So you can get in artifact mode, and then you can get in physics mode, and then you can get in parameter mode. So they ask the questions, they're all grouped together. That's one aspect of the ARMRIT registry that I really like. The ARRT, it's like pigeons playing ping pong. It's an artifact question, then it's TR, then it's patient care, then it's SAR, then it's artifact, and then, so they're ping ponging all over the place. All right, so what artifact is demonstrated here? Well, motion. What makes that motion? It's this repetitive bright and dark, and it happens to be in the phase direction here. So that's motion. It's a data sampling error. You can get it from gross patient motion, pulsatile flow, and peristalsis. Okay. Ways to decrease motion is you can put sap pulses in. Okay. You can swap phase and frequency. You can image faster. Okay. Here is, they'll show you this. What artifact is demonstrated here? Okay. This happens to be stir, and this is pulsatile artifact. So depending on what they say, if your best choice here is motion, then tell them motion. You're looking at that and you're going, that's pulsatile flow. Yes, it is, but it's also motion. So if they say what artifact is demonstrated here, motion, wrap, truncation, or chemical shift, the most correct answer is motion, even though you're saying to yourself, well, that's pulsatile. Yes, it is. But if motion is the best answer, tell them what they want to hear. All right. Some of the ways to decrease motion, you guys have already been through this at clinical. You scan faster as best possible. You can lower your TR, decrease your nex, lower the phase. Anything that brings the scan time down is going to make you scan faster. It will lessen motion. But don't forget, when you start doing all this stuff, you need to know the consequences of your action. So if you decide to drop your nex, you're going to lower your scan time, but you're going to drop what? Signal to noise. So this is where you need to know what your consequences are. There's some special motion suppression sequences. And they call it, the GE calls it propeller. The different manufacturers call it different, have their own names for it, but it's radial scanning. So the generic name for propeller, multi-vane, jet, blade, all those things is called radial scanning. And the way radial scanning works is you've got blocks of case space that are filled and they overlap. And the scanner is going to look at the overlap and see what matches and what doesn't match from one blade to the next, and it's going to throw it away. So it's cherry picking the motion right out of your image. And that's called radial scanning, radiating as in radius. So it's going around in a circle. All right. Some of the trade-offs for radial scanning is higher RF, because you're overlapping, you're repeating a lot of the lines of case space. So there's more RF. Here's an RF or a blade artifact. Maybe you guys have seen this before, maybe you haven't, but you can see how there's it's all those lines are pointing towards the center of case space. Okay, and that's called blade artifact. Here's that pulsatile artifact that I talked about earlier. Okay, and here's where you would use flow comp. This is stir, and you can see on the image on the right-hand side, the artifact is worse because there was no flow comp, and on the left-hand side, flow comp was turned on. So that's what flow comp does for you. But you might get something as easy as identify the artifact in this image, and you go, well, here it is. It's evenly spaced pulsatile. So it's motion, but it's really more pulsatile flow. But if motion is your best answer, tell them motion. Same thing, flow comp. You're going to see these kind of artifacts on typically long TR and long TE sequences, but you can also get them on T1s post GAD. Okay. RF artifact. Someone opened my scan room door while I was doing the scouts, and this is zipper artifact. Notice that they're in two different directions here. Okay. One is it's running top to bottom. This one is running right left. So we got our extraneous RF into the room during scanning, sometimes called zipper artifact. So why is there one down the bottom and two up the top? Are they going to ask you this? Maybe. The one up the top is a wide bandwidth of artifact that was received. Multiple frequencies came in. Here it was just one little frequency. So it looks like a zipper. It is in the frequency direction, but its location, okay? So you say, oh, it's an RF artifact, so it's going to be in the frequency direction. No, it's in the phase direction, but its location in the phase direction is frequency dependent, okay? So if it looks like a zipper, it's called the zipper artifact or RF. Here is wrap, aka aliasing, aka fold over. Okay, so we've got anterior abdomen that's outside the field of view and not sampled enough, and it gets misplaced. It's called wrap. They can use any one of those three terms, wrap, aliasing, or fold over. Why do we get wrap from tissue outside the field of view? Because it's not sampled enough. It's undersampled, and the scanner doesn't know what to do with it because the Nyquist theorem was not satisfied. We didn't sample those echoes enough to know where to put them. So they get put in the wrong place. Chemical shift artifact. Chemical shift is when we're trying to put too many frequencies in a pixel. A pixel can only hold a certain number of frequencies. Now, chemical shift imaging is another term for FATSAT. That's why I threw this one in here. Okay. So if you see the term on your registry during chemical shift imaging, blah, 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 they're talking FATSAT. It's a fancy name for FATSAT, chemical shift imaging. We are taking advantage with chemical shift imaging of the precessional frequencies of these different tissues. So there's a shift, there's a separation, there's a difference in the precessional frequency between fat and water. And that's called chemical shift. That chemical shift is going to get bigger or more pronounced at high fields. The chemical shift artifact, though, is when we're trying to put water frequencies and fat frequencies in one pixel, and they don't fit because there's too much frequencies. You're trying to put too many frequencies into a pixel. So what happens is those frequencies ooze out in the frequency direction. And I'm going to show you a picture of that right now. Okay. So we have a lumbar spine at 3T. You can see a dark line here and a black line here. That's in the frequency direction. That's chemical shift. Here's a much more pronounced example. This is also at 3T. This was during a lumbar spine, but you can see the white line here and the dark line here. That's chemical shift from trying to put too many frequencies in a pixel, and it oozes out in the frequency direction. Okay, that's chemical shift of the first kind. It's in one direction. So if there's chemical shift of the first kind, there's going to be chemical shift of the second kind, correct? Makes sense. So here is an abdominal study, and this is your dual echo or your in and out of phase TE. Here is an in phase TE. The protons are in phase, pointing in the same direction at TE. Down the bottom, this is your out of phase or phase canceled TE. Notice the black line around everything. Okay, that's chemical shift of the second kind. It is in the phase and the frequency direction. So it's in two directions. So that's chemical shift of the second kind, also called phase cancellation. Chemical shift of the second kind is what you're looking for in the abdomen, especially when you're doing adrenals. So chemical shift is going to be seen only in one direction. Chemical shift of the first kind, one direction frequency. It's in two directions for the second kind. Here's another artifact. Okay, this is called this is gradient warp. You've got in phase shift. So if you notice all this zebra stripe here, that's I'm sorry. This is Murray artifact, not chemical shift. My bad. Looks like chemical shift. So you see this zebra stuff down here on the top and actually up here. That's called Murray fringe or zebra artifact. And you get that on a very specific sequence called steady state gradient echo. And it's coming from RAP, phase cancellations, and drifts in precessional frequency. So fortunately, it only happens on the edges of the field of view, not right in the middle. And you could look it up if you'd like to, but this is the Murray artifact. When you've got geometric lines going in opposite directions, that's basically what you get. Okay, here's down the bottom right, bottom left, that's Murray artifact. All right. Here is Murray artifact. Once again, you look at this image, oh, that doesn't look too bad, but look up the top here. That's Murray. Gibbs or truncation artifact comes, it looks like zebra stripes. Gibbs artifact is also called truncation and zebra stripes. You get it at high signal intensity interfaces. So dark, bright, going into dark, and then going out to bright again. It looks like a zebra. It's called truncation. Very common to see it in the cord, and it's not unheard of in the brain. So here is truncation. It looks like motion, but it's not. If it was motion, it would be throughout the entire image. Truncation or Gibbs fades away as you get away from the high tissue contrast interfaces. I did it on purpose. I did a phantom on 3T, and I way knocked down the matrix, okay? 256 by 160 in the phase. Here's truncation right here. Looks like motion a little bit, but it's not, because phantoms don't move. At least the ones that I know of don't move, okay? Here is crosstalk, aka cross excitation. Now, for you guys who've had my classes before, I teach these as separate artifacts. Okay, crosstalk and cross excitation. Everybody calls this artifact right here crosstalk. It's really cross excitation, and it comes from stacks crossing each other in the back. Very common in lumbar spine, L5S1. If they say what artifact is demonstrated here, and they put crosstalk, then that's what they want. If they say cross excitation and that's the best answer, then tell them what they want to hear. Cross excitation and crosstalk is worse at T1 because of the TR. This is the exact same slice, the exact same patient, exact same overlap. Here's the T1. That artifact is going right through the cord. That's a repeat offense. And it's worse on T1 because the tissue here didn't have time to T1 relax. Here's T2 with the very long TR. It's there, but it's subtle. That's cross excitation. Here's cross excitation again. You guys have probably seen this. These are scouts in a breast with implants, and then down in the pelvis. Okay, crosstalk. Here's metal. This is a metal artifact. This happens to be a gradient echo image, and you look at this and you go, "Wow, that's a big hunk of metal." And yes, it is. Here's metal again. As we're imaging and we're getting closer and closer to the metal, the precessional frequencies get further and further away from normal. So outside here, we've got this is a T1 fat sat, and the precessional frequencies of the tissue out here is good. But as we get closer and closer to the metal, the precessional frequencies of the tissue close to the metal get worse and worse, and they drift. And see this little white comma thing right here? Okay, that's something called pile up. That's how you can tell the difference between metal and regular susceptibility artifact. Metal is going to have this white pile up, this white comma thing. Okay, here's somebody with metal in the pelvis. What artifact is demonstrated here? Here's that pile up, so that's metal. Or if you go, oh, that's metal, but what if the closest answer is susceptibility artifact? Tell them what they want to hear, okay? All right, I want to keep on going here. All right, magnetic susceptibility. Here is an image with magnetic susceptibility. This is old hemorrhage. Okay, this is the super paramagnetic stuff that I was talking about last night. This is susceptibility artifact. All right, what artifact is demonstrated here? This is corduroy artifact. You look at this and you go, wow, looks like you're looking through Venetian blinds. Yes, looks two different ways, but it's the same artifact. You got a spike or a bad data point in your K-space, and that's called corduroy artifact. Also called crisscross, herringbone, or spike. So any one of these guys can be applied here. Most commonly, it's corduroy. All right. Next one here, this is called anafact, and it comes from having, so here's the artifact right here, and it comes from having too many coils turned on for your field of view. So here's your field of view, and you got extra coils turned on that you shouldn't. So less is more. Last but not least is here's that proton density image here. Why are these blood vessels black? Any idea? Well, it's not an MRA image. This is called flow void or high velocity signal loss. What happened was the blood that was in these blood vessels when this slice was excited has moved on. It took its excitation with it, and unexcited blood has replaced it. So that's called flow void. Okay, so what happens is the blood was in the slice at excitation, and then unexcited blood took its place. So you're going to have bright image, but you're going to have dark blood. And last but not least, I believe this is the last one. And in the ARMRET study guide, they specifically ask about eddy currents. Eddy currents are these little black holes. See all this stuff? Those are called eddy current artifact. It's a ghosting in the small artifacts because you're causing little swirlies, for lack of a better term. Oops. You're causing, oops, sorry guys. Damn. Hold on. Bear with me for a second. Where was I? There I was. Okay.
This is important to remember when assessing risk associated with the item being exposed.
Okay, so we are causing we are causing gradients to go back and forth very rapidly, and what happens is you get little swirlies, little magnetic swirlies. Come on.
This is important to remember when assessing risk associated with the item.
Trying to turn the volume down. Anyway, but notice how the gradients are going back and forth very quickly. The gradients are being turned on and off very rapidly, and you're getting little magnetic fields that are swirling around, okay? And they're causing opposing magnetic fields, and you get these little signal losses, and those are called eddy currents. It happens in all directions. It's very common in your EPI sequences, okay? All right, enough of artifacts. Let's quickly blast through the scan time formulas and we'll call it a night, guys. Thank you again for your patience. Okay, so scan time formulas. There's three basic variations. You got one base, which is TR times phase times nex. So if they say to you, what is your scan time for this pulse sequence? They got to give you a TR, they got to give you a phase, they're going to give you nex. That's your basic scan time formula. So what you're going to do is you're going to multiply your TR times phase times nex. That's going to give you a great big number, which is your scan time in milliseconds. It's going to be a big number. Okay, then you're going to divide that by 60,000. Why 60,000? Because that's how many milliseconds there are in a minute. Okay, so let's do this example. In this T1 weighted sequence, blah, 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 blue, 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 TR is 500, your phase encodings is 256, and you're going to do 2 nex. Okay, so that comes out to 256,000 milliseconds. Cool. Now divide that 256,000 by 60,000. It'll give you 4.26 minutes. So is that 4 minutes and 26 seconds? No, it's 4 minutes and 0.26 minutes. How do you make this into seconds? You multiply 60 by 0.26. That comes out to 15 seconds. So call it 16. So this scan time is 4 minutes and 16 seconds. Let's do one more, a T2 sequence. So you're going to multiply your TR by phase times your nex. You're going to come up with a great big number in milliseconds. Divide that by 60,000, and it's going to be 11.05 minutes. Multiply 60 by 0.05, that's 3 seconds. Your scan time here is 11 minutes and 3 seconds. No one's scanning 11-minute, 3-second sequence. It's ridiculous, but trust your math, okay? That's how to do a basic scan time formula. The next one is going to be fast spin echo. The variation here is you got to calculate for your echo train length. TR phase nex, divide by your echo train, divide by 60,000. There's your scan time in minutes. So let's do that T2 that we just did, but let's throw in an echo train here, okay? So your TR times phase times nex, and then here's your scan time, divide that by 18, and then divide that by 60,000. And it comes out to 1.2 minutes. 1 minute and 60 times 0.22, 13 seconds. So your scan time here is 1 minute, 13 seconds. That's pretty easy. I'm going to keep on going. Now, the last variation here is for a 3D or a 2D sequential sequence. So remember I said yesterday, read the whole question, know what's being asked. So if they say, in this pulse sequence, what's your scan time? They give you a TR, they give you a phase, they give you a nex. If they give you something like partitions or, something like partitions or locations or slices, now you start saying, oh, that's 3D. If they say in this 2D sequential sequence, sequential is key, you're going to do the same thing. They're going to tell you how many slices. So TR times phase times nex times your number of slices or your number of partitions. Multiply that, you get 373,736 milliseconds. Divide it by 60. That 60,000 comes out to 6 minutes and 6.21 minutes. Convert it down to seconds. So the key term here is they might tell you 3D, and then you have to start looking for partitions. If they say sequential, then you have to, it's going to be parts or locations or slices. Okay. So just make sure you read the whole question and pick out the key words here. Okay. Questions, guys? I can see I lost a few of you guys in the interim. I'm sorry I went late, guys, but a lot of material to go over. Anybody have any questions? Okay, I got a thumbs up from somebody. Thank you very much. This is water. It's nothing more than that. It's not an adult beverage. That's coming though. Okay. That's coming. All right. Thank you guys for your time. I appreciate it. Thank you very much. Let me know when you guys take the ARMRIT or the ARRT, please let me know how you make out. I'd like to know. Thank you very much for your time, guys. And okay, what is that? Did I miss something here? All right, that was about concats. All right, thank you, thank you, thank you. Cheers. All right, guys and ladies, thank you very much for your time. Please email me if you have any questions. I've still got the same old email address. That hasn't changed. Jess, if you have questions, you can email me. You've got my email address. And thank you very much for your time, guys. Peace.
Bye, thank you.
Thank you.
Bye. Thank you.